Okay, let's just take a breath. I totally get that pre-exam panic. But listen, you've got this. You don't need to know every single little thing to pass this exam. Nope. You just need to know the patterns. And that's what we're going to do. We're going to hack this thing. So, the big exam is tomorrow, huh? And the pressure is on. I hear you. Well, you're in exactly the right place at the right time. We are about to turn that panic into pure confidence. All right, no fluff, no messing around. This is a speed run. High speed, high impact, everything you absolutely need to know. You ready? Let's do this. Okay, before we dive in, let's get one thing crystal clear. This whole subject, this massive, scary thing, it all comes down to one simple idea. It's just zeros and ones. That's it. Off and on. Everything else we're about to talk about, seriously, it's just a clever way to shuffle those zeros and ones around. So let's start right there with that foundation. This first bit is all about the language, the mindset of those zeros and ones. Nail this part, and trust me, everything else just clicks into place. First up, don't let this table freak you out. See that word radix? All that means is base. Super simple. You know, we use base 10, decimal, probably because we have 10 fingers. Well, computers only have 2 fingers, on and off, so they use base 2, binary. The one you really got to remember for the exam is hexadecimal. It goes all the way up to F, so lock this in your head right now. F is 15. Got it? F is 15. All right, next up is gray code. I like to call this the lazy code. And why lazy? Because it only changes one single bit at a time. It's like taking stairs one step at a time instead of jumping. This makes it really, really reliable. Oh, and it's also non-weighted, which is just a fancy way of saying a bit's position doesn't matter. The 1 is always just a 1, unlike in regular numbers, where the 1 in 100 is a big deal. Okay, parity. Easiest way to think about this. It's like a quick spell check for your data. We're looking at even parity here, and the rule is dead simple. The total number of ones has to be, well, even. So you just count up the ones. Is the count odd? Stick a 1 on the end to make it even. Is the count already even? Great, just add a 0 to keep it that way. That's literally the entire trick. So now we know the language of zeros and ones. What do we do with them? Well, we're getting to the absolute heart of digital electronics now, logic gates. And the best way to remember these? Think of them as security guards at a club. They're the ones making all the decisions. And here are the 2 main bouncers on duty. On the left, you got the AND gate. This guy is strict. He will only let you through, that's an output of 1, if you and your friend both have ID. No exceptions. Then on the right, you got the OR gate. He's the friendly guard, super chill. He'll let you in if you or your friend has an ID. One of you is good enough for him. Okay, lean in for this one. This is a sentence you need to burn into your memory for the exam. If you forget everything else about gates, remember this. NAND and NOR are universal gates. Why? Because you can build any other gate you want just with a pile of NANDs or a pile of NORs. That's a guaranteed exam question right there. And last but not least in our guard lineup is the XOR gate. My trick for this one? Just think of it as the hater. It absolutely hates it when things are the same. If the inputs are different, you know, a 1 and a 0, it's happy, it gives you a 1. But if the inputs are the same, 2 zeros or 2 1s, nope, it gets angry and gives you a big fat 0. Okay, so we've got all these logic gates. Great. But what happens when your circuit has like 100 of them? Well, it gets complicated and expensive. So this next part is all about the puzzle. How do we make our circuits simpler, which also means cheaper and faster? Let's check out the tricks. First trick in the book is De Morgan's theorem, but forget that name. Just call it the break and change rule. It's this simple. You see a long bar over everything? Just break the bar in the middle, then change the sign underneath it. A dot for AND becomes a plus for OR. And poof, you just made the logic simpler. All right, next up, the K-map. Please do not think of this as math. Think of it as Candy Crush for digital logic. Seriously, your only goal is to find the biggest groups of ones you can. And the groups have to be in powers of 2. So groups of 2, 4, or 8. Bigger groups are better. And here's the pro tip, the secret level. The map wraps around. The left side is touching the right side and the top is touching the bottom. Don't forget that. Okay, let's switch gears to a new type of circuit. These are called combinational circuits. And the key thing to remember about them, they have the memory of a goldfish. Their output only depends on the combination of inputs they're seeing right now. No memory of the past. What you put in is what you get out instantly. And the classic examples of these are adders. You've got the half adder, which is pretty basic. It just adds 2 bits together. But the full adder, that's where the magic happens. It adds 2 bits, plus it can take in a carry bit from a previous calculation. You know, just like when you're doing math on paper and you have to carry the 1, that's what the full adder does. So it's really adding 3 bits at once. All right, check this out. The multiplexer, or MUX for short. The absolute best way to picture this is a train station. You've got a bunch of trains on different tracks. Those are your inputs. But there's only one track leaving the station, the output. The select lines are like the signal operator, flipping the switches to decide which one of those trains gets to go down the main line. Okay, this is where things get really cool. What if we want a circuit that can actually remember stuff? Well, for that, we need sequential circuits. Unlike those goldfish brain circuits we just saw, these guys have a memory. They have a brain. Their output depends not just on what's happening now, but on what happened before. And the absolute, most fundamental building block of all of this memory is the flip-flop. That's it. Its entire purpose in life is to be a tiny little memory box that can store exactly 1 bit of information, a single 0 or a single 1. That's it. Think about that. Every song, every photo, every app on your phone is just billions of these tiny little boxes working together. But like with anything, there are good designs and bad designs. The first try, the SR flip-flop, had a major bug. If you gave it 2 1s as input, it would just crash. It would enter this forbidden, invalid state. Total disaster. So they invented the JK flip-flop. It's the fix. When it gets 2 1s, it doesn't crash. It does something smart. It toggles. It just flips whatever bit it was holding. And to make the JK flip-flop even more foolproof, they came up with the master-slave setup. Just picture a boss and an assistant. The master, that's the boss, listens for new instructions only when the clock is on. But the assistant, the slave, only acts on those instructions and gives the output when the clock turns off. This simple 2-step process stops the circuit from getting confused and tripping over itself. It's brilliant. Okay, deep breath. We have covered so much ground. We've hit all the big concepts. Now for the home stretch. This is your final cheat sheet. The last-minute tips you need to remember when you're actually sitting in that chair staring at the exam paper. You will probably get a question about logic families. Here is everything you need to know boiled down. TTL? Think of it as old-school muscle car tech. It's super fast, but it is a power hog. It will drain your battery in no time. CMOS. That's the modern stuff. It's what's in your phone. It's a little bit slower, but it just sips power, which is exactly why your phone can last all day. And now for the ultimate, final, secret weapon exam hack. Listen closely. If your mind goes completely blank on a question, if you can't remember the words, draw the symbol. Seriously, examiners award points just for drawing the right shape. AND gate, it's a big letter D. OR gate, it's a curved shield. MUX, it's a trapezoid. Drawing the picture can snag you some easy points, and sometimes that's all it takes. And that's it. That was the speed run. See, it's not about memorizing a whole textbook. It's about knowing the patterns, the analogies, the little tricks. You know this stuff now. You really do. So close the books, get some sleep. You are ready. Now go crush it.